Okay, so we're going to carry on now with our discussion about derivatives. This is now section 2.4. And I mentioned this the other day that this is really one of the most important concepts in all of calculus, the chain rule. And so we'll be using that today. Now, before we do that, I'd like to point out that the chain rule has its own unique type of notation that we need to get used to, which is not nor which is pretty normal in calculus. Many concepts in calculus have multiple ways of being expressed, and this is no exception. So they're starting us out with this physics example. I think we can pass over that and start with something completely different. Um, so we'll start by noting here that we have two different ways of expressing a derivative, at least, that we know of. And the ones that we're most likely to use are f prime of x and dy dx. Well, it turns out that for certain applications, this dy dx notation can be very helpful because we can actually decompose it into a product of two other derivatives. And you'll see, we'll do plenty of examples of this as we go along. And we can rewrite it as dy du times du dx. So we're not going to do this just yet, but when we do, you'll see that this is an extremely helpful way of finding very complicated derivatives. So then, of course, over here we have f prime of x. And so what we'd like to do today is introduce the chain rule. And here's the formal statement of it using this notation. But what I'd like you to see here is that what you're actually doing here is taking the derivative of what we call a composite function. Now, you may remember we did this fairly recently. And so there's different composite functions we could potentially create. One, of course, is f of g of x. We could also solve for, let's say, g of f of x. Let me just quickly, oh, sorry, hold on. That's better. Okay, we also could have g of f of x. And then it can really get interesting. We could have f of x. We could have g of x. And we can also have a composite function consisting of even three or more functions. For example, we could have f of g of h of x or something like that. So the number of possibilities is endless. Now, let's remind ourselves, how do we calculate or construct a composite function? We'll start with a simple case. Let's say that f of x is 2x plus 1. And let's say g of x is 3x squared plus 4x. So why don't we solve for f of g of x just to remind ourselves how this is done? What you're going to do is go to your f of x and replace all the x's with g of x. And then make the substitution. And then, of course, multiply it out. And that's it. We're done. So and of course, we could also, if we wanted to, go ahead and find g of f of x, but I just want to remind you how this process works. So what you're seeing here is that the chain rule is actually a method for finding the derivative of a composite function. That's what it's for. Okay, so this is what we're going to be doing with the chain rule. And I would like to point out that we can apply it in a couple of different ways. We also could use or find the derivative of g of f of x, and that would be g prime of f of x times f prime of x, as you would imagine. Okay, now what they would like us to do, I think they've got an example here for us to work on. Let's try, let's say, let's keep it simple. Let's use this one. Okay, now we know how to do this, but um, here's the trick to the whole thing. You have to recognize that this can be written as f of x is x cubed. And then you let g of x be the x plus 2, so that f of g of x would be g of x cubed, which would in turn be x plus 2 cubed. That's the starting point. We have to recognize what function, what's the, when you look at this setup, you've got two functions. And if you remember, we called this the inner function and the outer function. So we have to make sure we define it correctly before we try to apply this rule, this so-called chain rule. And so the way it works is this. All right, now based on the functions we have here, f prime of x would be, based on the power rule, 3x squared, and g prime of x would simply be 1 because it's x plus 2. The derivative of x, as you know from our discussion last time, is 1, and the derivative of this constant 2 is just 0. So what you've actually got here is this. Okay. um, and then we replace the g of x with its definition, x plus 2. And that's the final answer. So the derivative original function was y equals x plus 2 cubed. The derivative is 3 times x plus 2 squared. Okay. Now, this is the kind of thing we're going to need a ton of practice, and we'll get it. Don't you worry. But in a nutshell, that's what it's all about. Now, here they're showing us, they're reminding us again, this notation. If um, For certain cases, though, it might be easier to use this approach. It depends. It depends on what you're looking at, but both of these will give us the same answer. And if you're going to use that approach, the way they want you to think about it is this. We're going to assume that f of g of x can be written as f of u, where u is a function of x. Then du dx is the same thing as g prime of x. Okay. And f prime of g of x is f prime of u. All right. Now you're starting to wonder, why are we doing this? Doesn't it make things 10 times more complicated? And again, it depends. Like here, for example, oh, and so finally, if you do all that, the final result here is And we can write it as F. Oh, actually, what they're doing is writing it like this. And then y prime, which is the same thing as dy dx, is the same thing as f prime of u g. Wait a minute, what did they do there? I think they made a typo there. That should just be u prime. All right, but anyway, let's go to an example. Um, dy dx y equals x squared plus 1 cubed. So the first thing we do is let u be x squared plus 1 so that y can be written as u cubed. Okay. Well, now, what do we do next? Well, we need some derivatives here. Um, dy dx equals, all right, so let's go back and revisit what we've done here. If we let y equals u cubed, and in turn, u equals x squared plus 1, then dy du is obtained with the power rule. Whoops. That should be 3 minus 1, of course. 3u squared. And in turn, du dx is, again, based on the power rule, 2x plus 0, which is just 2x. So the final result here would be you're literally just multiplying them together. 3u squared times 2x. But now, if you notice, we got two different variables mixed together. But we do remember that u was defined up here as x squared plus 1. Wait a minute, x squared, that's right, x squared plus 1. And that's your final answer. So in other words, the original function was x squared plus 1 cubed. Let's write that down somewhere. That is the final result. That is our chain rule. Okay, so we could have done this just as easily with f prime of g of x, um, g prime of x, and you would have gotten the same results. So this way, they want you to see the two equivalent ways of using the chain rule, but the bottom line is you'll always get the same thing. Okay, now like I said, Um, we're definitely going to need a lot of practice with this. It takes a while to get used to it, but once you get the hang of it, you'll realize it's pretty straightforward. Okay. And you're saying, no, we don't believe it for a minute. No, you will. Once you've done enough of these, you'll be fine. By the way, I don't know if you noticed it or not, but if you look in Brightspace, which should have here open somewhere, at the end of this chapter, and all the chapters for that matter, what I've helpfully done is included, which we'll go over soon enough, as soon as this chapter is over. Um, here we go. So this was chapter one. Oh, that's because it's preliminary. Okay. We have chapter one here. And then the one we're in now, chapter two, at the very end, I've got review problems. What are they doing there? Well, I think that in case you're not getting enough practice with the book and with the videos and WebAssign, I've got problems that should help learn the material. And we'll go over these as soon as we're done with chapter two, just to get you some more practice. So you can start working them right now if you want. In fact, let's open up chapter two review problems and see what's in there. And these are exactly the kind of things you'll have to do in WebAssign, but also on the exams. So for chapter two, you can see it's just a lot of derivatives, and we did all of these cases. And you notice way at the end we have the chain rule. This is something that hasn't come up just yet. This will be, I think, in section 2.5 or maybe 6, what's called implicit differentiation. And so if you can do all of these techniques, you're in pretty good shape. And I mean really good shape, because this is what chapter 2 is all about. So this will give you an opportunity to get even more practice. So you can start working on these anytime you want. But then when we're done with chapter two, whatever video that happens to be, I'll go over these and show you how they're done so that you get even more practice. All right. And of course, before any exams, we'll review too. So let's see, what do we have here? So here's an interesting one. The general power rule, if we're going to write it in terms of dy dx, we have u of x to the n. We're going to wind up with n u of x to the n minus 1. So far, so good. But then we need u prime of x, or du dx. Okay. Now, if you notice, the reason why this is necessary is because u is a function of x. So if you had instead, let's say, x to the third power, then dy dx, based on the power rule that we learned earlier, would be 3 times x to the 3 minus 1, or 3x squared. Okay, because x is a simple function. If instead we had something like this, now we need the general power rule. So u is x squared minus 2x du dx is 2x minus 2, applying the power rule that we know. And so therefore, it's going to be n and the n is 3. U of x is x squared minus 2x, n minus 1 is 2, And then all that gets multiplied by this 2x minus 2. And then you can simplify it if you want, but that's the bottom line. Okay. So again, we'll get plenty of practice with these, but what starts happening here is that you're applying the power rule to a more complex function. Instead of x cubed, for example, it's a polynomial raised to the third power. And that's why suddenly we need this du dx term at the end. All right. Now they're going to give us one in terms of f of x. Same thing. F of x equals 3x minus 2x squared cubed. Okay. Now we're going to let this be u so that f of x is actually u cubed. Um, which in turn is what you see there. Now, when we take the rule derivative, actually, if you want to be super technical, we should write this as u, not just u, but u of x. But and then du dx, we can attain it with our normal rules. 3x to the 1 minus 1 minus 2 times 2x to the 2 minus 1. 3x to the 0 is just 1 minus 4x. Okay. So we make all our substitutions. And that's the end of it. That's our general power rule. Yeah, they just left it like that. Okay. So it doesn't really matter if you call it f of x or y or whatever. You're going to get the same thing. Okay. Wow. Now here, what they're going to do here is start to show us some strategies for maybe taking some of these horrendously messy cases and turning them into something much more manageable. It's not always easy to do this, not even possible, but you should try whenever you can because you never know when it might reduce to something much easier to work with. So here's their first example. And what are they going to have us do? Okay. Hmm. Well, all right. At least in the beginning, there's really not a whole lot we can do. Now, we are about to apply the product rule, and let's just remind ourselves how that works. Whoop, let me do this real fast. All right, so the same thing is going to hold here. What they're going to do is this, say, listen, this is a product of two other functions. It doesn't really matter what we call them. But what we do need to know is um, the derivative of this first function and the second function. So we'll start with this one. So with x squared, now we need the derivative of this piece. So what we have here, now remember, we're applying the general power rule here. It's n u of x, n minus 1 du dx. So that means it's going to be 1/2 is our n. U is 1, let me write this over here. And that implies a du dx of minus 2x. So now we just basically plug everything in. We've got 1/2, 1 minus x squared to the minus 1/2 times minus 2x. Now that's just this first piece. Then we still need this piece, gx times f prime of x. That would just be 2x. So let's bring this all together. Plus, okay, I have a feeling this is where the simplification is going to come. Because if you notice, both of those terms have a common factor. Oh, I just realized this should be a negative 2x. Sorry. Yeah. Okay. So, you end up ultimately with, what do they want us to do? Hold on. Just want to make sure I'm not messing this up. We've got x squared, 1/2, 1 minus x squared to the minus 1/2, negative 2x. That's fine. Plus 1 minus x squared to the 1/2, 2x. All right, we're good. Oh, wait a minute. No, this one isn't negative. Sorry. I was wrong about that. I had it the first time. So what exactly do they mean for us to do then? I think they want us to factor out. Okay. So I'm not sure if this is really necessary. They want us to factor out. That would be, see, we've got this. No, that can't be right because they don't both have an x squared. Um, here's why. Hmm. I think they're just unnecessarily complicating this. Let's do that one more time. We have um, x squared, 1/2, 1 minus x squared to the negative 1/2, negative 2x, 1 minus x. I think they probably skipped some steps. They've simplified that. You notice how we have here a half and negative 2. Um, no, I guess they didn't factor that out. But Okay, I think what they did was they multiplied these, but then there's a half here, so that means, oh God, what a mess. So they multiplied out the x squared, the half, and the negative 2x. And what's left, now this one, you notice the problem here is that this is positive 1/2. So I'm not really sure what they think. I don't, all right, let's just not waste any time with this. We got the right answer. That's the bottom line. I think there's no real need to simplify it. Um, I mean, you can see why you might want to simplify it a little bit when it's possible, but right now, I think they're just making a bigger mess out of it. But this is the correct answer. And I guess here they're doing the same thing. Jeez, look at that. See, and then again, you notice how they insist on using these very messy examples right off the bat, which I think is ridiculous. Let's see. Maybe we can make up one of our own. All right. Let's see. Why don't we start out with a much nicer example just to get the ball rolling? What if we had this? All right, that should do it. So then n is 3. This is the n right here. U of x is what's inside the brackets. And using the power rule from previous sections will give us 12x squared plus 4x. So therefore, applying the general power rule, we're going to have n u of x, but now to the n minus 1. And then that all gets multiplied by du dx. So we end up with, and that, I mean, unless you want to multiply it out and simplify it, that's your answer right there. Okay. Now, see, why couldn't they pick one like that? Um, Look at these things they chose. All right, but we'll get back to this and we'll do plenty more of these. What do we want to do now? Let's see what comes next. They have trig functions. All right. Now, this is exactly what we did before, but with instead of x's, we have u's. That's, and those u's are assumed to be functions of x. All right, so here's what I mean. So we know that the derivative of sine x is cosine x. But If it's a sine of a function of x, that's a completely different matter. Instead, now we need to not only have the cosine of x, but du dx. Although they've written it as u prime, it's the same thing. I prefer it this way because it's more obvious. But so in other words, if you had something like this, and so what you'd end up with is this. And if you want, you could write it like this. So that's what separates this from what we previously did with trig derivatives. In those cases, we were restricted to just x. Here it's a function of x. So you need to take into account that derivative du dx when you're done with the calculations. Other than that, the rules are exactly the same. You might remember, for example, minus sine x. So therefore, that would be the result of taking the derivative of cosine of u of x. So if you had something like that, you'd end up with minus sine. And then you need here the du dx would be 6x plus 2. And this is something we did in the previous class. We're applying the power rule and the sum rule to come up with 6x plus 2. And that would be your final answer. And then we have all the others. These are the same ones we went through the other day. What's different now is that it's a u, or u of x, instead of just plain x. Oh, so they do have a few of their own. Okay. Sine 2x, for example. And then over here, du dx would simply be 2, right? Or if you want to follow the rule very closely, it's actually because there's a 1 here, an implied 1, it's 2 times 1 times x to the 1 minus 1, which is 2 times 1 times 1, which is 2. Okay. So therefore, what do we have here? Oops, no, sorry, it's the sine, cosine rather. It's usually written like that. Um, okay. Then we might have something like this. Cosine x minus 1. The derivative based on the power rule is just 1 because this is implicitly x to the first power, 1 times x to the 1 minus 1, which is just 1. And of course, the derivative of a constant is just 0. So dy dx over here will be the negative sine But that happens to be a 1 in this case. So we end up ultimately with minus sine x minus 1. Okay. And then what about tangent 3x? Now, you may not have this one memorized. The tangent, uh, derivative of the tangent is the secant squared. It's 3 secant squared 3x. Okay. So they've got some summaries here. By the way, now they have to do this to me. Um, they've mixed into here even more notation that we haven't seen before. I don't know why they have to do this. I'll show you what I mean. The product rule, where did those U's and V's come from? Oh, all right. So here's how we have to think about it. The product rule can be written in two equivalent ways. We already know one way of writing this. But what they sometimes do is they replace this with a U and this with a V. And then, if that's the case, then G prime of X would be written as V prime, and F prime of X would be written as U prime. So this would end up being uh, so it means the same thing. I don't know why they have to mix and match the notations. And then same thing with the quotient rule. They've got a version over here that's got U's and V's. Let's remind ourselves how that works with f of x and g of x. Okay, so that's the quotient rule. But if we do the same thing, we let u equal f of x, v rather, is g of x. That implies that f prime of x is u prime and g prime of x is v prime. Oh, not squared, prime. So that means I can rewrite the quotient rule as well, it's a little bit simpler, I suppose. The only problem is I've got to be so careful here because otherwise my V's and U's will start to look exactly the same. That's better. Okay. So in other words, this is just another way of expressing the same idea. So this little table could potentially be very helpful to you, but you just have to get used to the way they keep changing the notation, but it gives us the same results. And then they did the same thing now for the trig functions. Whoops. We had these with just x, but when you replace that x with u of x, or just plain u, oh, okay, they didn't put it back in. It's here, this one. Okay. All right. So these are examples that require us to use the general power rule and the product rule. Wow, look at them. Wow, what a mess. I'll tell you what, I think what we should probably do these together because they're such a mess. But hmm, I'm thinking that maybe it would be easier if you practice these first and then we'll go over them together rather than trying to run through them right now because these are kind of messy. I mean, the answers are here, but they don't show you how they got them. So we did something like that in the last section. I think what we'll do is next time we meet, we'll go through some of these knowledge checks, and then we'll get back into the new material. And this is the end of 2.4. So we still have 2.5, implicit differentiation, which is a little bit different. And then 2.6, related rates. This is an application of derivatives. Yeah, you get the idea of factor high school geometry. But and so what I'll do is we'll go back and revisit some of these knowledge checks, and then we'll go through those, and then we'll carry on with the new material. So I think that's a good plan. And all right, so I'll see you next time.